So today we're going to talk about vectors in space. So in the plane, each point is associated with some ordered pair, x, y. In space, each point is associated with an ordered triple. So a point in space is some point x, comma, y, comma, z. That is an ordered triple. Okay. So though through a fixed point called some origin, so we call this fixed point O, the origin, 0, 0, 0. We've got three mutually perpendicular lines. Now, we've got the x-axis, we have the y-axis, those are perpendicular to each other, but then we also have the z-axis, which is perpendicular to each of those. Okay, so they're all three perpendicular to each other. Okay. The direction chosen for each positive axis makes the system the right-handed system. So what does that mean? So this is the positive axis for x, this is the positive axis for y, and this is the positive axis for z. The right-hand system, so to remember, your pointer finger, your thumb, and then your arm here. Okay, so when you make that shape there, you can see those are the positive axes. Okay? So what's highlighted in red, that's the positive axis. That's the right-hand rule, which states that if the index finger of the right hand points in the direction of the positive x-axis, the middle finger points in the direction of the positive y-axis, and the thumb points in the direction of the positive z-axis. Okay, so this is pointing in the direction of the positive y-axis there. All right. So associate with each point P an ordered triple of real numbers, coordinates of P. For example, the point 2, 3, 4 is located by starting at the origin and moving 2 units along the positive x-axis. Okay, so let's try to graph this. So the right-handed system looks like that. That's x, that's y, that's z. So I'm going to go 2 units, 1, 2, along the x-axis. And then the next part, I'm going to go 3 units in the y direction. 1, 2, 3. Okay. And then I'm going to go 4 units in the z. 1, 2, 3, 4. Okay, 1, 2, 3, 4. So z kind of looks like this. The red X kind of looks like this. And then the Y kind of looks like that. And so this point, so let me try to shade this a little bit, see if this works out. So that's the red side, top side's the blue side, and then this side's the pink side. So this corner here that point right there is 2, 3, 4. You can kind of see in the three-dimensional right there. So this point here is 0, 0, 4. This point over here is 2, 0, 4. This point down here is 2, 0, 0. This point over here is 2, 4, 0. And that point is 0, 0, or actually 0, 4, 0. This point over here, I guess, is 0, 4, 3, 4. So let me change this real quick. That's a 3. And this one is 3 as well. Okay. I think I got it now. All right. And then that point down in there is 0, 0, 0, the origin. Okay. So, points of the form x, 0, 0 lie on the x-axis. Okay. Points of the form 0, y, 0 lie on the y-axis, and 0, 0, z lie on the z-axis. Okay. Now points on the xy plane are of the form x, y, 0. So this is kind of what we're used to. So we're used to the xy plane. If this is x, this is y, this is z. So points on this plane would be kind of like this. Okay, so you can kind of see what's going on here. Okay, this would be the scenario where z is equal to 0. Okay. All right, so this would be the equation z equals 0. Okay, that would be the xy plane would be z equal to 0. Okay, so that's kind of the idea there. You can think of the xy plane as a sheet of paper, and the xyz is kind of three-dimensional space, like a cube, like what we have going on there. Okay, so same thing if you had the yz plane. The yz plane would be 0, y, z. Okay, and what would that look like? Well, that's x, that's y, that's z. So the yz plane will be like this sheet going through just like that. So let me do red. Okay. So it's kind of like this red here. Okay, so that's the YZ plane. Okay. So, and it stretches out infinitely in all the directions. So that would be the equation x equal to 0. All right, and then you can do the same thing for the xz plane, and that would be y equal to 0 if you wanted to run through that game there. Okay? Now, finding distances between 2 points in space is kind of intuitive. All right, so distance formula in space. Okay, it's very similar to the distance formula in on a plane. Okay, so if I have some P1, which is x1, y1, z1, and P2 equal to x2, y2, z2, those are 2 points, then the distance d between P1 and P2 is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. See how similar that looks? That's the distance formula for ordered pair. Now for ordered triple, we just add in the z's. z2 minus z1 squared, okay? We're literally finding the magnitude between these 2 points, P1, P2 here. Okay, that distance, right? So let's find this using a problem. Say P1 equals -1, 3, 2, and P2 equals 4, -2, 5. So to get the distance, I take the square root, and I'll do the x's, then I do the y's, then I do the z's. So 4 minus 1 squared plus 3, sorry, plus a -2 minus 3 squared plus 5 minus 2 squared. Now it doesn't really even matter the order in which you subtract, because when you square it, the negatives go away. So as long as you do your x's with your x's, your y's with your y's, and your z's with your z's, you're good to go. So when I do this, I get 5 squared. So 5 squared plus, and then this is another -5 squared, and then this is 3 squared. So this is equal to a square root of 25 plus 25 plus 9. So this is a square root of 59, whatever that equals. Who cares, right? That's just the distance between those 2 points. Okay, so distance. So maybe you're asked to find the distance between P1 and P2. Okay, so that's what's going on there. All right, now you might be asked to find the position vector. Okay, so the position vector in space, so you have some x, some y, some z, so x, y, z. So your unit vectors are I, and you've got j, but you've also got this thing, you've got a new axis, that z-axis, so we need another letter, so we're going to use k. So I, j, and k, okay? So to represent some position vector that goes out to this point right there, we start at 0, 0. And so if this is the point A, B, C, then this vector would be equal to AI plus BJ plus CK. Okay, so that's the idea there. So if you want, you can bold in your unit vectors. Okay, your book does a little bit bolder, so I might try to make this a little bit less bold. There we go. All right. So to to represent the vectors in space, we introduce the I, J, K. Directions are along the positive x-axis, the positive y-axis, the positive z-axis, respectively. If v is a vector with initial point at the origin and terminal point at this point ABC, then we can represent it as follows. So initial point at origin at origin 0, 0, 0 and terminal point at A, comma B, comma C. Then this is the position vector. Okay? So the scalars A, B, and C are called the components. So A, B, C are components. Of the vector AI plus BJ plus CK, with A being the component in the I direction, B being the component in the J direction, and C being the component in the K direction. So a vector whose initial point is at the origin is the position vector. Okay, so the position vector, initial point at the origin. Okay. The next result states that any vector whose initial point is not at the origin is equal to a unique position vector. Okay, so how do we do this? It's the same idea we had in 2-space. So we got our theorem here. Suppose V is a vector with initial point P1 equal to x1, y1, z1, not necessarily at the origin, and terminal point P2 equal to x2, y2, z2. Okay? If V equals P1 to P2 vector, then V is equal to the position vector. Well, how do I get the position vector? I just take off x2 minus x1, I, plus y2 minus y1, j, plus z2 minus z1, k. Okay? And that's all there is to it. So in a picture, what does this look like? So you have your x, your y, and your z. And say you have some x1, y1, z1 starting point here, okay? And it ends at x2, y2, z2 here. If I'm literally going to copy this and shift it down here, then how do I get to here? How do I get to 0, 0, 0? I have to subtract off each of those pieces to make that all go away. So I do that for each initial and terminal point. And so that's where that x2 minus x1 comes into play for the first component. y2 minus y1 comes in play for the second component. And z2 minus z1 comes in play for that last component there. Okay? So this here is the position vector. Okay? All right. So finding the position vector. So let's just do an example and make sure we got it. It's not that big a deal. I want to find the position vector of v equals p1, p2 if point 1 is negative 1, 2, comma 3, and point 2 is 4, 6, 2. So all I need to do is subtract. So my vector is 4 minus a minus 1 I. Where's the I component coming from? It's coming from the first parts. Okay. And then the next part is 6 minus 2j. Where's that coming from? It comes from the second component. And then I have the 2 minus 3 for my k right here and right there. So whenever I do this, I get 5i plus 4j plus a negative k. Okay? That's all there is to it. So that is the position vector. All right. So performing operations, if I have v equals a1i plus b1j plus c1k, and w equals a2i plus b2j plus c2k, be two vectors, and alpha is a scalar, then what happens? Well, v equals w if and only if a1 equals a2. So these components are the same, those components are the same, and those components are the same. b1 equals b2, and c1 equals c2. All three of those have to be all three have to be true. Okay? And then they're the same vector. Now, v plus w is equal to adding the sum of the components, the a1, a2, I plus b1 plus b2, j plus c1 plus c2 times k. Okay? Subtraction, same thing. It's the first one, a1, minus the second one, a2, I plus b1 minus b2, j plus c1 minus c2, k. Alpha, a scalar, multiplied by v is alpha times a1 I plus b1j plus c1k, which equals alpha a1i plus alpha b1j plus alpha c1k. It distributes to each piece there. So each component sitting right there. And then the last, the magnitude of the vector is the square root of a1 squared plus b1 squared plus c1 squared. The components squared, the sum of the squared components, and I take the square root to get the magnitude. Okay? So the definitions, if I put these into practice here, not that big a deal. So let's go ahead and we'll just go ahead and do it. So example, v equals 2i plus 3j minus 2k. and W equals 3I minus 4J plus 5K. And I want to find V plus W. Easy enough. I add 2I plus 3J minus 2K plus 3I minus 4J plus 5K. Add the components that go together. Let me do it different. So 2I and 3I make 5I. Okay. 3J minus 4J gets me minus J. And then negative 2K and 5K make plus 3K. Okay, no big deal for that one. Now, this one's not too much harder. V minus W. This is 2I plus 3J minus 2K minus 3I minus 4J plus 5K. So the negative distributes. So I have 2I plus 3J minus 2K minus 3I plus 4J and then minus 5K. Okay? And so what does this get me? This gets me minus I plus 7J and then minus 7K. Okay? No biggie. All right, let's do scalar product. So let's try to find, once again, V equals 2I plus 3J minus 2K. And let's do a W equal this time. Let's do same thing, 3I minus, minus 4J plus 5K. And I want to find 3V. So to get 3V, I multiply 3 times 2I plus 3J minus 2K. And I get 6I plus 9J minus 6K. Okay, distribute through just like you'd think. Now to get 2V minus 3W, okay, what I'm going to do is I'm going to take 2 times 2I plus 3J minus 2K, and I'm going to do minus 3 times W, which is 3I minus 4J plus 5K. So I get 4I plus 6J minus 4K, and then this becomes minus 9I plus plus 12J, and then minus 15K. And so collect my I's, I get minus 5I. Collect my J's, I get 18J. And collect my K's, I get minus 19K here. Okay. So I wanted to find the modulus or the magnitude of V. So V, let me copy it down here so I don't forget. So that's V there. So to do this, I take the square root of 2 squared plus 3 squared plus negative 2 squared. And I get square root of 4 plus 9 plus 4. 4 and 4 is 8 plus 9 is 17. So that's the square root of 17. Okay. Now recall the unit vector. A unit vector has a modulus or I keep saying modulus. Let me call it the magnitude. So the unit vector U has a magnitude equal to 1. In many applications, it's useful to be able to find the unit vector u that has the same direction as the given vector v. So to do this, I take hold of the fact u equals v over the magnitude of v. Okay, this is a unit vector that has the same direction as v. Very powerful. Okay, so say you have some vector v here. If I want the unit vector, maybe the unit vector just goes out this far. That's the unit vector in the same direction as the original v vector, but its magnitude now is equal to 1. Okay, where this magnitude might be pi or whatever, whatever it is. Okay, so using this formula, this tells me that v is equal to the magnitude of v times the unit vector. Okay, so I want to find the unit vector in the same direction as v equals 2I minus 3j and then minus 6k. So to do this, I need to calculate the magnitude of v, which is the square root of 2 squared plus negative 3 squared plus negative 6 squared, which equals square root of 4 plus 9 plus 36, which equals the square root of 49, which is 7. Now, to find the unit vector in the same direction, okay, I'm going to take unit vector equals v over the magnitude of v, which is 2I minus 3j minus 6k divided by 7. So that's 2 over 7I minus 3 over 7j minus 6 over 7k. Okay? And this, my friends, is that unit vector there. Okay?